So basically, start. I think recording is there, but let's just wait for a sec. What I wanted, what we have to start talking about is context switch, right? So what? Like just quick reminder, which is obviously you guys already know what's going on. But again, so we're building this tiny microphone, which modulate the fact that we're like a couple of weeks behind. Oh, by the way, homework. So Jerry actually, who was our volunteer to create the autograder, just pushed it just a second ago, and so I think it's all ready to go. And you guys can let's set the deadline. I mean, I talked last time to a bunch of people after the class, and it seems that it turned out to be a lot harder to finish this homework, and so sure, let's just take our time. And look, for some people, probably it's actually honestly not as hard, but if you don't know Rust, just you feel confused about almost everything. And what is the name? Oh, and so it's a little hard to finish. And so, okay, let's assume Monday is a decent deadline. And so Jerry essentially pushed those submit instructions. So let's take our time. It has some autograder, essentially. It tries to test your allocator, and let's see if it's broken. There is a chance, but it works at least for his solution, right? So that's reasonable plan. Monday with an autograder. How many people have finished already? Josh, one. You and Jerry, good job. Yeah. Sorry, just got it. Yeah. So what I was saying that I'll do my office hours tomorrow, but I will have on Zoom, unfortunately, so I cannot do it in person, most likely, because it's still minor chance I will be able to do it in person. But the idea is the following. So we're building this microkernel, despite the fact that we're like a couple of homework behind, like at least in a class, we already know how to create an address space for this very first process with an L file. And from which we loaded as part of loading the kernel and some additional file from the grub. We know how to do syscalls as of last time. And then, I mean, maybe our understanding is not really fully complete yet, partial maybe, but still, just imagine we have. And okay, sure. An obvious next syscall is to gate. So we already had one which allows us to create process 0. Now, obviously, we want to do create process, right? Create a new process. And we discussed it a couple of times, the possibility of how we can do it. So someone maybe remind me real quick, how do we want to create new processes? Probably you shouldn't look at me. Just minor epilepsy, right? Sorry. Yeah, so what's the plan for creating processes? Meaning that we want to have the next one running next to it. This is P0, we'll create P1.
I remember you said that there would be a bootstrap program that's small that would be running in the new process that would set up its permissions and whatnot.
Oh, well,
yeah, something like that.
But then yeah, but then I came up with an even simpler, I think, solution. What's the, like, again, we're on top of a microkernel. So if this is our microkernel, ideally we don't want we don't want to put any like linking loading in the microkernel. And the argument here is like everything can be done at user level. So I just wanted to clarify, it's very simple actually, so nothing super hard.
This is what you were talking about.
Right, yeah. So no, the question is like, okay, the end goal for us, right, obviously, is to have an L file sitting here as well. So we have to solve a couple of questions, like where does this L come from? Like, I don't know, we don't have a disk driver yet. I mean, we can argue, let's say build it, but maybe it doesn't make that much sense. And so one would argue that probably this ELF file somehow will be a part of this P0. So like turtles all the way down, ELF within an ELF. But why not? Like we can soup it here, right? That's the easiest way, literally, because like we had one ELF file which the bootloader placed in memory, and it's ELF of domain 0. And I mean, you see, ideally we should come up with some kind of a file system abstraction here, but and I don't mind it, but let's our file we can have something covered. But essentially at a high level, we say, look, ELFs of other processes are sitting here as well, right? As part of domain 0. And why not, right? Like some special section, FS section, will make sure that compilation works, right? And so when we created process 0, all of it got loaded into this process 0 address space, and we started running inside it. But that's like there is some real ELF here, so that gets executed, and there is some storage section .fs which keeps the other process images, right, or binaries, or if we want to be like really clever, it has to be some kind of a in-memory file system, which is not very hard to build, right? But just to keep it simple, we can think of it as a file system, but real implementation can be just whatever, something really simple. But okay, so that's a reasonable plan. We will have this ELF sitting in process 0. The question is, like, when we create a new process, we need this ELF to show up here, and it has to be, as you say, either we need some kind of a trampoline which relocates this ELF, or it has to be ready to go, and then we'll just start executing, similar to how we did with process 0. So what would be our create process system call, which can achieve it? Looking for the simplest possible solution, but also elegant, arguably. What should be the interface of this syscall? I mean, just again, it's a very simple sentence. Don't over. There is an ELF here. Make sure it's here. So, and well, with some additional here that it's ready to run, or
kind of related, but like, is there gonna be like parents and children? Or are you not worried about that?
wow, yeah, that's not bad. That's a good idea.
Because if that's the case, you'd have to give your ID to it, I think.
Well, if there is a parents and children, which we can choose whether we want to support something like that or not. Let's discuss it later. That we probably can push in a microkernel, because if it's part of access control, then maybe we can't trust userland, or we can push parts of access control to userland as well, honestly, but we're separate discussion. But
so if the parent process already has the ELF, could you just pass it as a buffer?
yeah, I would agree that this is the most straightforward approach. So this create process system call takes a pointer to this ELF in some kind of a bufferish form, which essentially encodes the star and size, right? Agree? And what happens next? What's the semantics of the system call? How do we?
The kernel copies that memory to the child process's memory.
The kernel creates a new address space similar to how we created P0, and copies this ELF into this address space. So which probably means that we also have to pass virtual address where it has to go, right? Because the ELF itself.
That feels like something the kernel should know and not the users?
Well, if then you need to parse the ELF here. And we can, but maybe, and then you restrict yourself to just doing the ELF. But what if the idea is that this guy, actually the parent can do the linking, for example, and arrange all the sections like in memory already, prepare everything for running. And then just say, look, like copy all of it here. Or alternatively, you can always fix that it starts at a specific address. Like essentially the design choice here is to say, look, instead of passing this virtual address, we fix it to some way. And then we'll user base. And we only guarantee that we will copy this out at user base address. That's also fine. And then if we want to make something more sophisticated later on in this address space, we can do some kind of a self-linking or self-relocation or and self-relocation step. And then like really, if this is just some kind of a container, which comes maybe as ELF or collection of trampolines and ELF, then we will just relocate and create those sections within this address space, right? So it's either parent or kind of like then more closer to what Axel was saying. We pass some thing and it would say it has to run at a specific address. That's fine too. I agree with this. Maybe we can go this route. So this way, the expectation is that everything what gets passed is just copied directly at kernel base address. And I agree with that. So probably that's a better solution, and it simplifies the system call itself. You say, look, it just always goes into one address, right? And makes sense. It seems like a reasonable design choice. It's almost like, you know, starting a virtual machine and you just passing the kernel binary, and it just starts booting itself. And it just like you assume that the kernel which you loaded in this address space is linked at a specific address and can start going. So essentially, some piece of it is statically linked, and then you can implement some dynamic linking later on. Makes sense, right? So that's kind of an elegant way to do it. And then one other thing which I wanted to happen is that the result of the system call is the parent. It returns an endpoint. So an endpoint is like a kernel object which allows parent and a child to communicate later. So meaning that if the parent wants to, if the child has to be connected to some other processes in the system, then the parent can connect them through this initial endpoint. But that seems to be sufficient. So this interface essentially create a process start, like some bufferish representation of an ELF file inside. Parent gets an endpoint, and if anything, they can implement a communication protocol walking through this endpoint. And if endpoints are still not clear, we'll spend some time talking about them, right? So then we will get a second process, and probably as part of this create process, similar to how we didn't discuss it, but inside create proc1, we had to create a thread of execution, at least one within this address space, and create one here in this address space. Call it T0, T1, or whatever. Great, but they are like they live within, like threads are not like visible outside of their processes, right? Right. Okay, we have this story, then we're pretty much almost there. And now these two guys are ready to run. And the subject of our topic of our discussion today is if you have a CPU, how do you switch between them? So how do you context switch, right? Because if we do context switch, and fill in the gaps with those system calls, we almost kind of get the system which is usable, right? The only unfinished piece will be this communication endpoint, but even this, you know, like roughly speaking, you know, if I don't need my processes to communicate, I don't even care about it, right? So, okay, so cool, makes sense. That's the kind of the plan for the next couple of lessons. Okay, so context switch, right? So how can we build it? So what's the plan and what needs to be done?
Is it at a high level saving the current process state, loading the new process state, and then yeah, I think that's it, right?
More or less, I agree with this, but yeah, the devil is in the details. Okay, let's answer a couple of questions like what can trigger a context switch? At some point, what we're doing here, we're also kind of discussing the execution model of our kernel right now. Because really, you're saying, okay, you can come up with the kernel in which the context switch is triggered in one specific way, or maybe in another, or maybe in both, right? So let's quickly think about when do we want to trigger context switches? Obvious, yeah. Yeah, on a timer, which means roughly speaking, you're running inside one process, like maybe in some kind of like infinite loop here. And the hardware raises the timer interrupt. And then we should somehow react to it, and we'll discuss how. And in the end, probably in the end of this timer interrupt, we would like, as Talia said, save the state of this process, of this thread T0 somewhere in the kernel, pick up the state of this thread T1, again, somewhere from the kernel, and just essentially make sure that we exit here, and we will do IRET here. The instruction pointer will point to some instruction which was previously executed in this thread T1, right? Make sense? Okay, so we're going to talk about it. So timer. The questions here which are worth discussing are, what if this guy was not running at user level, but was doing a part of a syscall? Can we preempt it with a timer or not? And this again, those are design choices and which we will make, right? So okay, let's think for a sec. So are we okay preempting execution of a thread within the kernel, or we don't want it?
I guess you'd need to change the privilege level to make it safe.
What do you mean? Because we
Well,
are already in the kernel, we are ring 0.
Right, and then you'd be switching to a different process in ring 3. So you'd need to save the kernel stack that you were in, the ring that you were in, maybe the GDT that you were using. I don't know if you need to.
That's correct. So you need, okay. No, that's correct. But do we see? Yeah, meaning that if we started executing this one T1, at some point we'll come back to this T0. We should like, and if it was preempted right here within the kernel, obviously we shouldn't return and start. Like if it did like syscall instruction here, we shouldn't return past the syscall, we should, or add the syscall, we should return back to this kernel address, right? So, but this seems fine. So if we're saving the state of a process as a collection of instruction pointer in a code segment, then that shouldn't be a problem. It seems that should work uniformly. As long as you load this to, you save and restore this to, you will find yourself in the same privilege level, right? Yep. So, but okay, hold on. What I wanted to, and okay, let's maybe park it here for a second. Like this discussion of whether we want to allow preempting our threads inside the kernel or not. But back to the reasons maybe, or not the reasons, but how else we would like to possibly trigger a context switch. What would be another reason? Priority. But for example, give me maybe more. Priority kind of implies that we have a scheduler which maybe tracks some priorities of threads globally. And under what condition you suddenly say that you want to switch from T1 to T2?
Blocking, sleeping, stuff like that.
Yeah, so I agree. What are you really getting to? Like in some cases, like maybe similar to what Manowik said, where you detect a case where maybe you were executing some code and maybe you created this T2 thread. I just created it. I don't know how to write it. T2 equals. And like it happens that the semantics of your code is such that at this point you say, look, T2 is a higher priority, and no matter what, I will try start running T2. Like immediately or almost immediately give up execution of T1 and start running T2. And what we're going to do is something like, maybe you'll have an abstraction of something like a yield function call, which yields the CPU from T1 to T2. And this also similar to what Axel is saying, where I can't imagine immediately the case where you do an IO in the kernel because device drivers run in user level. So device drivers will be here. So this will be this device driver, right? So it will just it will do configure maybe a DMA read from this disk, but it was at user level, and you say, look, but guys, like I'm such a good code that I will not be just waiting here, sitting for the DMA to complete, but I will do an explicit syscall in the kernel, and internally the kernel will yield the CPU just unconditionally. So it's similar to this one. It's that instead of this, like the T2 is created, T1 says, okay, I will invoke a yield system call because I just know that I'm not going to be doing anything forever and for some time. And then T2 will, like, the system can pick any other thread in a system. So essentially implement some kind of a scheduling logic, maintain some metadata, maybe like a list or tree of all runnable threads, and says, okay, T2 is the next one to run, and then does a yield, and then as part of that yield switches to T2, right? So, but like essentially conceptual difference between these two is that yield will be sitting somewhere inside your code, like inside the syscall or inside maybe when you like just created new inside another syscall like you, or whether this one will be triggered asynchronously by the time, right? And the difference is that when you yield intuitively, what's supposed to happen? More colors. Orange. Like if you're doing a yield, then syscall starts executing from T0, and imagine it's a yield syscall. Then we switch to T1, and we kind of exit on T1, right? Whether there's a timer, this T0 was executing somewhere here, timer starts running through the kernel, and it will, instead of returning when you supposedly you're done with the timer interrupt, when you do the IRET here, you really should switch from T0 to T1 and start executing something inside T1. So it's kind of like slightly different, right? But more or less, this is what we want to build, right? Does this make sense? This is actually very similar to what x6 is built. Does anyone remember how context switch works in x6? I figured already who was in that class, x6 class. 1, 2, 3, 4, 5. 5. Everyone else is super brave, right? That we signed up for this class was out. Okay, so someone from that x6 class, can you remind me how it works in x6? Do we remember? Oh, we're kind of very close to the discussion. No takers. Okay, and that's why I, on purpose, kind of like already, I have like let's just walk through the slide deck from.
Is it switch the notorious part of the original V6 that Ken Thompson said you're not expected to understand this?
I don't know. It's very simple. So this, let me share my screen real quick. Wait, what's the context here, Talia? He said that it's so hard that you're not supposed to understand.
So inside switch in the original V6, there's a comment that said literally you are not expected to understand this. It's some very niche interaction between the old C and PDP-11 hardware.
Oh, maybe that I don't know. No, never heard this story. Like, don't spend that much. Okay, hold on. This is the, like, roughly speaking. Okay, let maybe make sense to start from here. So the first thing which we want to discuss. This is again x6. What I'm showing here, important state, which is worth remembering for this specific setup, which we will repeat. So there is a kernel stack here. Like let's say in x6 it's 4 kilobyte, and in our Rust kernel it will be some number of 128 kilobytes or more, right? And there is user level processor. So there is a boundary between user and a kernel. There is user stack somewhere here, right? So everything is normal. We're running in user level, right? And the case which we want to consider is what happens when the timer interrupt hits us, right? So essentially, roughly speaking, that's the state of our system. We have GDT somewhere in memory, like similar familiar sections, user code, user data, kernel code, kernel data, TSS. There's a CR3 points to the page table. Green part of the page table is user accessible. Yellow part is only kernel accessible, so similar to how we are building it in our microkernel as well, right? And then, like not surprising, like back to interrupts. Interrupt comes. Imagine it's a timer. Again, everyone did configure interrupts and interrupt controllers, so we all know we would configure timer, which is 0 to be delivered as vector 32. So the hardware picks this vector 32 from the IDT. IDT is pointed by this IDT register, which we loaded on the CPU, right? Familiar story, although this is 32-bit, but it's the same in 64 bits as well. So you have a code segment pointer, which points back to the GDT that allows us to select a kernel code entry with privilege level 0, right? Again, TSS register points to the TSS. This link is kind of missing here on the diagram. TSS points to the kernel stack. Imagine we're not using IST stacks for now. Remember IST stacks, this interrupt stacks, just regular IDT stack or regular TSS stack. Hardware just pushes this 5 things on a stack, on this kernel stack, like stack segment, stack pointer, flags register, code segment, code pointer of the user, right? So essentially whatever was here. And like from the IDT, we pick up in like pointer to the interrupt handler, In our case, it's vector 32, and the hardware starts executing there, and we switch from privilege level 3 to privilege level 0, just because here, which we configure with PL0, right? Makes sense? Like that's everything as we did in this class as well. And then interrupt handler starts running in x86. They are normalizing the stack by pushing the error code. Since interrupt doesn't push the error code, they just push 0. In order to distinguish later on between which interrupt we are currently processing, they push the interrupt number, which is number 32. They jump to their all traps general, like save the state thing. And right now our kernel stack will look something like 5 things pushed by the hardware, 2 things pushed by just this vector 32 code, right? We're jumping to the all traps. All traps as it's kind of similar to our, like, again, what happens here is that we were benefiting from Rust macro system. x86 just writes it by hand. So instead of like having a make function, they wrote an assembly function, just linking against it, right? And so here they just say, okay, we will have a generic piece of code which saves all the state. So they start pushing all the segment registers, DS, ES, FS, GS, push all with one instruction, which pushes all the general registers. We usually do that as part of the timer interrupt, right, in our code. Since we're now running in a kernel, we only switch stack segment and the code segment, right? Because these are the only 2 things. Like the code segment comes from the IDT from here, the stack segment comes from TSS, right? So those 2 are ready to go with PL0, but we actually like don't even know, probably in x64 bits, you don't even have to do this, but they essentially loaded it with like essentially saying, okay, cool. It's all like kernel data will be DS and S, NFS and GS will be also kernel data, right? And at this point, they are ready to invoke a C function of the kernel, which is generic trap handler. They, like again, in 32-bit system, on 32-bit systems, the very first argument is pushed on a stack. So essentially, that's why they push this stack register itself, meaning that they essentially like creating this pointer to the current stack. So you pushed all the state on the stack, and that's their kind of like trap frame information thing. And instead of like pushing into this, what is it? RDI, RSI, what is the first argument? I forgot. 64-bit. RDI, one of these 2. Essentially, they push it on the stack, and at this point, they can call a C function. Make sense? Okay, so like essentially this call calls a C function. The trap frame is passed as the first argument here, right? And what we're doing here is okay, like some time accounting, but essentially the end goal of this is that this code here. So they say, okay, if there is a process which is in the running state, and we are like processing a timer interrupt, let's do a yield, meaning that let's yield the CPU from this currently running thread to another thread, right? Okay, sure, that's very similar to what we were trying to discuss on the timer. Enter on one timer interrupt, go into yield, and what they are doing in x86, it's a little weird. So they actually implement a scheduler as a separate thread, which meaning that they always have this thread, which they call a scheduler, running on the CPU, and then scheduler switches to process some process I. And when the timer interrupt comes, like in this case, they always somehow first switch to the scheduler thread. And then the scheduler picks up the next thread to run, maybe cleans up this one, and then switches to like process K, for example, right? So effectively, x86 does 2 context switches, right? Which is a little odd because it's probably not necessary. what we can guarantee is that there is one thread, which is this thread in which we booted. We can call it, I don't know, idle or something. Always exist in the system. And essentially, even if the last thread, if this P1 from which we're switching away is exiting, we can switch to idle and clean up its state. It's essentially like what they are doing. They switching first to this scheduler function, and this scheduler function switches to that scheduler thread, right? And literally that scheduler thread does some scheduling and switches back to the process, but we probably don't have to do it. So essentially, if we are running on a thread right now, what we can do, like essentially we create this diagram. So we were running on thread 1, timer interrupt came, we're running through the kernel, we can pick a victim, kind of like pick another thread from a queue of existing threads in the system and just directly switch to that thread, right? That's kind of like a slightly better idea of doing it, because then you don't have to switch twice, you just switch once, right? Makes sense? And then essentially when we switch, we will exit on this thread, IRED, and then start executing T2, right? If T2 is our victim, right? Or like if this is like a from thread, this is 2, right? Make sense? So essentially just slightly simplifying. But let's just take a look at, okay, let me ask you a question. Okay, so far so good. So it was borderline straightforward, right? So we just like, we handled the timer interrupt and we invoked a method which we call yield. And the expectation is that yield, after picking the victim to switch to, will invoke some low-level function which finalizes the switch. And when this function switch returns, it will return to T2. Like essentially, if somewhere in the past, T2 was preempted at some instruction A, right? Its instruction pointer was pointing to this instruction A. So switch will make sure that this T2 starts executing from this instruction A, right? Make sense? Okay, if I ask you a question, so how can you pull this? How can you pull this part of the context switch to make sure that we somehow save all the state of the T1, and then what is really inside this function switch, which switches to T2? And I mean, I just wanted us to think a little bit about it before showing the code. It's actually not as hard. Did anyone coded context switch before? No one. Which is fine, but okay, let's try to break down this problem into pieces, right? So I'll make a larger drawing just to make sure that we understand. Like, if this is P1, get preempted by a timer, and we're running, so when we're running with a timer interrupt, right? What we need to observe here that some subset of this T1 state is already saved. In fact, all the user registers are saved as part of this like data structure, which x86 is called interrupt frame, right? Because the hardware saved the first 5 things which contain stack pointer, RST, stack segment, R flags, RAP, which point, like which points to this, some position in the user, yeah, right? And code segment, right? Makes sense? So these 5 are already saved. And then we carefully crafted, and this is like, since you already coded the timer interrupt, you already did it, right? And then you save all general registers here, right? Whatever, RAX, I forgot the order, RBX, R15, right? So this also is sitting here, and we saved it carefully, making sure that we're not going to lose the part of this code, right? So when we reach this yield function somewhere here in the kernel, and the expectation is that, like, internally yield will call, I mean, maybe yield will invoke the scheduler, will give us like the thread to switch, let's say T2, and at some point we will invoke this low-level function switch, which arguably should take T1 as an argument, and we're switching from T1, which is from, and T2 as an argument, which is two thread to switch. What is left? Oops, sorry. What is left unsaved, or what needs to be saved in this switch function?
So it sounds like that this is using a lot of the code we wrote.
Correct. So all of it is written because timer interrupt you already wrote.
Yes, so we have the state saved, but instead of doing an iret back to T1, we would push new values to the stack such that when we do iret, we go to T2. Then my question is, it feels like a stack, feels like the values for T1 shouldn't be on the stack end, because the scheduler wouldn't necessarily want to return to T1 in the order that it is on the stack. Like,
Great question. So the question which you are bringing up is design choice of how many stacks we want. So obviously there will be a user stack for each process, right? Or for each thread of execution, right? For each thread. Okay, cool. So this is the RSP is pointing to this stack, right? When we get pushed into the kernel, we say that there is a kernel stack. And these things are saved from this kernel stack, right? When they start executing yield switch, all of this is like pushed here, yield and switch. And this is the kernel stack. The question is, do we want to share this kernel stack across all the threads in the system on this CPU, for example, whether the stack is per CPU or it's still per thread? Because if it's per thread, like in x86, it's totally fine to remember it, like in some thread data structure, have a pointer to the top of the stack, RSP, and switch to a new process. And this not new process, new thread of execution, right? And this new thread of execution, let me draw it maybe green, will also have its own kernel stack. And will also have its own user stack, right? And so, like, if you imagine that something similar happened to this T2 in the past, whatever I call it here, T2 in the past, then its stack is also kind of in a similar shape. So it has a drop frame, and then it has whatever, some, maybe it's not yield, maybe it was like some foo and some bar, but then somehow maybe we again yield it, and then some switch as well, right? Which means that it will have its own, if we save here RSP, SS, R flags, RIP, so there will be RIP, which points of, not to the kernel stack of this, not to the user stack, to some kind of user code section, right? and this RSP will be pointing to this user stack, right? So what I'm trying to get to is that there's certain symmetry between these two, because this process had some cost, right? And we context switch away from it. But if we leave it in a specific well-formed state, then it's totally fine, as long as we have this invariant that each thread has its own kernel stack. We're free to save this state, right? And it's a little easier to think about it this way. And then we can think about additional optimizations. If we say, look, embedded systems, we don't want to waste the whole stack. I'll suggest you a way for how to get rid of it, right? But for now, this makes sense, right? So this answers your question.
Yes.
This previous question.
Can we have as many kernel stacks as we want? Or are we limited to the 7 ISTs?
Hold on. Okay, great question. So is there an answer in the audience? In the room? I mean, again, what are those sevens? Like again, don't get confused. If this is our TSS, TSS just has 7 entries, which point somewhere to some stacks. And this, like, we can call them IST stacks. But in this example, we even don't use, we're not even using IST stacks. We're using stack, which is for, I forget exactly what they call it, like what kind of letter they write on it. Let me just quickly look up. I wanted to zoom in here, but I cannot zoom in. They call it kind of like ESP0. So let's call it RSP0. And that one was this error when we were, this guy was pointing right here, right? Because this is from where the hardware started pushing. Make sense? But nothing prevents us from, first of all, TSS is TSS, I forget exactly, it's entering the TDT, right? Nothing prevents us from first creating like a pointer, I don't know, to another TSS, or alternatively changing this pointer to point to some other location in memory, right? And so you can, as long as you have memory, you can always have as many stacks as you want, but only one of them is active, meaning then you put it inside the TSS, and what makes it active is that the hardware, if there is another interrupt, the hardware will save some data on this, right? Like right here. Make sense? So this number of those stacks is not limited to anything. You can play games with those 7 IST stacks, but arguably, you probably will just have them per CPU. And we will talk more about it, but per CPU is just fine. Right? Makes sense? We're still following? So roughly speaking, what it means is that when we context switching to a specific process, we probably want to update the field, this RSP0 field in the TSS section to point to the kernel stack of this specific, I keep saying process, I apologize, specific thread, right? Make sense? Actually, maybe stop sharing and make sure that we have a diagram. So far, so good. So everyone is on board. Yeah. Right. So wait, back to symmetry, right? If each thread in a system has its own kernel stack, then we always will leave a thread in this state in which the kernel stack is somehow well formed, and we can kind of start kind of almost like returning from this stack with the goal to eventually exit to user level, right? In fact, when we create the very first thread, which never ran, we can just make it up and just say, look, like, let's just fake it and just, the switch will return to some stop function, which will just do IRAP and just goes to user level, right? This is what x86 is doing. But back to this idea. So we're running on T1, white collar. We timer interrupt, we tick to victim by calling maybe a scheduler, and it gave us like T2 as a target. We're gonna switch from T1 to T2. Intuitively, if we kind of zoom out a little, this is the state of T1. This is the state of T2 as we left it some time in the past in this state, right? And what needs to happen since I switch then? Just again, looking at this diagram. Remembers. Okay. It's reasonably simple. But wait, hold on. What state do we have to like? If we ever, okay, imagine we want to come back to this thread T1. What state we need to save to make sure that we can kind of like smoothly. It's almost like at some point we will return from this switch later on in time when someone context switch back to us hundreds of milliseconds later. What state we need to save to make sure that we can keep running? Yeah.
The kernel stack address.
Which is where you want to.
Well, you've got this one stack per process.
Correct. Okay, sure. I agree with this. So in our thread data structure, like again, we can build the system like there's a process data structure P. Process has a list of threads. T1 is one thread of a P, right? Of a process. Process has a pointer to a page table, right? Because it's an address space and it's shared between all threads. Maybe we'll need some metadata to keep the layout of the address space around, right? But okay, T1, we said will have its own kernel stack. So we probably want to make sure that we remember this pointer to the top of the kernel stack, right? Because we want to load it and back into this TSS here, right? Cool. Okay. Page table is already saved, right? What else do we need to save? So page table saved, kernel stack. We just said, okay, sure, let's save it. There will be a pointer. Do we need to save like user stack? Pointer to the user stack.
No, because that was pushed to the kernel stack when it entered.
Correct. Because we already like, yeah, we saved it here, right? So we have this pointer. We don't even care that much about it unless we want to change something in the stack, but we can get it. Instruction pointer is also saved here, right? User registers saved. What about kernel registers?
You need to save CR3 because that stores which page table you're using.
Well, but you already have it inside the process data structure. So you will just load this pointer. Okay, like let's be very, very specific, not abstract. We're reaching this point. We're entering the switch function. Imagine the switch function is an assembly function. At this point, at the very first instruction of switch, let me just write it here, switch. What state is unsaved?
Yes.
GS. GS. Why GS specifically?
I feel like I'm just guessing, trying to read your mind. So I don't know.
No, hold on, wait. Why do you read my mind? It's like imagine there is some register file. And I assume that you guys already like heard this story before, which have some registers. RAX, RBX, RCX. No, roughly speaking, you say, look, guys, I don't really, I cannot read his mind. Let's just save all of them again, right? Why not? Like, that's safe approach. So you say, if I save all of these registers, then for sure I can come back later and start running this thread. And if I restore instruction pointer, clearly, depending on what, like how I set up this like interaction, I will exit from switch back, right? Make sense? So do you agree at least with this claim that if you save all the hardware registers, like on entry to switch, and then you say, look, I imagine switch takes two arguments, a pointer to, like, imagine each thread comes with some additional storage for those registers, RAX, RBX, and so on. You on entry on when you enter switch, you have a pointer to this register file of T1, and you have a pointer to a register file of T2, right? So let me just enter the blue line. I know will be split in between, but this is register file of thread T2, right?
But I thought that when it entered the kernel with the trap frame, that the trap frame stored all the general purpose registers. Or I mean that our assembly trampolines would store.
Correct.
So why are you storing it
Again,
additionally?
and that's a good question and a good design choice. So the question is that, like, maybe I was executing some function, like some foobar function in the kernel already. Maybe.
Oh, because it's executed some code in the kernel and it needs to resume with that code.
Correct.
Like it's executed up to the point that the switch line is
Right, but there is some work left undone here. Or maybe in a more general case, since we said, okay, look, guys, we allow when this thread was executing, maybe it was already executing in the kernel to begin with. It was doing a syscall, and then it was preempted by the timer interrupt. And so as part of this foobar syscall, we actually want to continue, right? Makes sense? So, but I can show you a case when you don't have to do this and you say just like whatever. If you make a decision that the kernel doesn't have any state, doesn't save any state, that's also a valid design choice, but let's discuss it later. So, but again, back to this idea. If you save all the registers in some storage, right? And you say, look, my code on the entry to switch was like, I don't know, like move RAX into this whatever storage, move RBX, right? And so on. And at some point you say, look, I reached the switch point, and at this point you say, look, like, guys, I will start restoring from that storage, which like from this one, from the T2 storage into like whatever R15, and you do all of them and you move into RAX, roughly speaking. Then when you do, if you never touched any stacks, so part of it will be RSP, so you're already on a new stack. If you do read from here, then since your new RSP is pointing somewhere here, you just return to a switch, or like at some point the assumption is that the switch was called by T2 and you start returning here, and eventually maybe return into the kernel and then eventually into the user. Make sense? Or it's already confusing? Yes, no? At what point you lose me? Or I lose you? part. No, but wait, bear with me. So like switch, saving code the registers. Start like first saving, then restoring, then read, since you restored RSP, already goes to a new stack, right? So you kind of halfway through this saving, restoring, your hardware RSP register gets flipped from here to here, right?
So you can do a regular read, not an read.
Oh, you have to do a regular read if you want to return back to the kernel, which in most cases makes sense, right?
I thought switch didn't return to the caller of it. I thought it returned to T2.
Yeah, it does return to T2.
Okay. I'm missing how you changed the instruction pointer to be T2.
How they like my instruction pointer, I assume that it was saved here as part of the like return value.
So you just pushed all of T2's data onto the stack, and then ret will return to T2's address.
Well, I don't have to push it on a stack. I can save it anywhere. I can save it as part of the thread data structure. But if this data structure for RSP value, it contained a pointer to this stack, I will automatically restore it, right? Makes sense. And so my ret instruction will return to the stack of T2, right? Like if you're too confused about the kernel story, think of it as, I mean, I keep using the word continuation, but I don't know if it makes it any better, but like effectively stack encodes the future of this computation, right? Of T2's computation, because it's the future is I have to return, maybe execute some code inside yield, then return from here to bar, maybe execute some code like after like bar called yield. So I will bar called yield. I obviously return somewhere here, execute some code inside bar, then return from bar into foo, execute some code inside foo, then foo says, wow, actually I'm returning to user level. So it does IRAP, returns to user level moves forward, right? But in a way, the stack is it captures bits of the past, but really it captures the future, right? And there is nothing really like you say, okay, sure, you're trying to like completely blow our minds, but really not. Like it's like regular computation itself pushes stuff on a stack, right? At any moment of time, you say, look, like there is some kind of a stack here. Imagine there is a magic primitive here, which I call switch, but it will like a magic wand or something. And this switch says, okay, well, hold on, freeze myself on this stack and pick a different stack. And of course, since someone was running on this other stack, maybe some kind of a full bar computation, say, look, this computation was frozen either with an explicit switch or, yeah, roughly with an explicit switch. Then it will start continuing, right? And you can switch between the stacks. And as long as you have a stack for each computation in the system, you can switch between those, right? And it doesn't have to be in a kernel. This is how you build those asynchron types, right? So you say, I forget exactly how the syntax goes, but imagine you have lightweight threads of execution in user level, and you say, like, let's switch to a new one. So just save your state on a stack, and then you golden, you will come back to it. Runtime handles the stacks, and you go to a different one. Right? Makes sense? Oh, okay, so at what point the story breaks for you? I get it, it's a little unusual, but if this is my magic lamp which suspends myself, like, I don't know. I mean, maybe Jahang uses the word park or something for this. If it parks you saying that, okay, I enter this function, it saves all my state on this blue region, And it, by the way, remembers my stack as well. Right, so that's fine, I can come look back later. That's the context switch.
Like all that stuff was pushed by the trap. After that, you want to save all of that stuff again in special thread data structure. I don't understand why you want to save it all again in special thread data structure. Everybody else does. That's okay.
No, it's a good question. So, like, roughly speaking, this part is just related to the fact that, like, imagine the simplest case of context switch. The simplest case is that, let me just, like, I need some space here. So, imagine you have just one synchronous primitive, meaning there are no interrupts. Imagine you have a, just anywhere in your code, you can build it in like user levels. You have foo, and then you say switch, and you have, I mean, and maybe you switch to bar. That's a good question. Like, how do you know? But imagine somehow you create these two computations, and they are represented by stacks, right? Imagine it's just a tiny runtime. You just coded it up. Your code looks something like create a thread of execution, and you pass a function foo, and like it never ran before yet. And so your runtime just literally pushes like the entry point of foo on this stack, maybe no state, or maybe some additional, like maybe it also has all the registers. You say create second thread of execution, you pass bar. So you're roughly speaking creating two threads with entry points, foo and bar, right? At user level, but it's plain C code, nothing, no kernel, nothing. This points to here, right? And you say, at some point, you say something like schedule, or you say something like switch, and you passing yourself like this thread of execution, which also has a stack, for example. You say, you call it current, and you're switching to foo. The runtime says, okay, sure, I will save your own state on your own stack. Let's put it, I don't know, somewhere here. And I'm switching to foo. Foo never ran. It starts running from the entry point, executes, reaches the switch statement. At this point, it like says, okay, so let's switch to, let's say, bar. The current currently points to this stack. So it saves all the state of foo on this stack, switches to bar, bar never ran, starts executing bar function, right? But it's like nothing, no interrupts, nothing, just everything is like what is called cooperative threading. Bar starts running, reaches the switch statement, again, has some notion of a current, which is bar, which points to this stack, saves state of bar on this stack, and switches to just, let's say, foo, right? Of course, runtime picks foo stack and continues running inside foo, right? For example, here. And that's logical to continue. You don't want to start new from scratch. And now imagine everything is in the loop, right? And this one is in the loop as well. And so you will stuck in this ping pong, meaning that you again switch, you save your state, switch to bar, bar switches to foo, and so on, right? At some point you say maybe exit, like after some iteration of the loop. And well, what happens to exit? Exit maybe picks the next thread, which which is on this queue, right? And imagine there's only one bar or maybe two like this one, which imagine this one is waiting in a join statement, right?
And that's, the advantage is another user space, normal C.
It's like started in mini. The kernel knows only about this one, but it's cooperative threading on top of user level. And it created two threads, and join is just call to the runtime, meaning that, okay, I'll wait on this two to finish, and then I will continue my own execution. Every time you try to run join internally yields to anything on a queue saying, I'll give you a chance to run, and then later on, hopefully you will finish. And at that point, this one says exit, goes into the runtime. Runtime says, okay, who is the next to run? It's this main thread. And at this point, you finish with join and continue running, right? So this you can code in C, and I can give you a code to do this, right? But the idea is the same. The switch is the magical primitive of the runtime, which means that you just coded it up in assembly. It will just pushes your state of where you were. And maybe it's not just foo, maybe it's like a stack of functions which you called from foo, right? Then you remember where you were and you keep running, jumping between these two. So that, right, but those are like two different threads effectively. So the same stuff happens here. And roughly speaking, this first part was just saving the user state of the process. And after that, it's all just this. So we are in a kernel, no switches, privilege levels. We just kind of like hitting the switch primitive, somehow similar to how we hit it here. Like if foo was running in user level, we don't care, we just saved it already, right? And we're just jumping between switches in the kernel space.
It almost feels like what you're saying is like once you enter that call to switch, you can't access like that trap frame in white. Is that kind of what you're saying? That's why you have to sort of make it anew once you enter the switch. Like,
not exactly. Okay, unfortunately, I probably should stop here. So because it's 15, 16 minutes up. So let's come back to this. Yeah. Up. I can start this story again. The question. So, okay, then we'll finish next time. But we'll recap. But you'll get this idea. Maybe I will start with this one again. So with a concrete example for how to build this one. And then maybe it will be easier to understand what else needs to be saved. It's actually quite simple.